Good afternoon, everybody. So today we will continue our discussion on conservation of momentum. In particular, conservation of momentum is used to solve collision problems when two things bump to each other. So there are two types of collisions that we will discuss. One is called elastic, and another one is called inelastic collisions. So we will use those collisions as example to show how we can use conservation of momentum to solve those problems. So as we left with our previous class, conservation momentum has a very similar format as the conservation of energy, right? If you have a change in the momentum of your system, if you have a change, then that can be accounted by the momentum transfer, right? P in or P out. I didn't write P in minus P out because momentum P is itself a vector. So whether it's the momentum in or out doesn't really matter as long as we keep the vector sign on it. So if there's a change, there must be a momentum transfer into or out of the system. So as we recall, to transfer energy out of the system, we need to do work, right? It's the force applied for a displacement is work that can transfer energy. Likewise, external forces can transfer momentum. And we call this transfer, give it a name called impulse. So just like how work change energy of a system, impulse can change the momentum of a system. So how do we calculate impulse? Hopefully, this will already give a clue by looking at the units of a momentum. You guys still remember, right? The units of the momentum is the units of m times v, right? And this is kilograms meter per second, and there is also newtons times seconds, right? The work, the unit for work is newton times meter, and that is corresponding to the energy unit for energy, which is joules. So if you apply a force over some distance, you can change the energy of the system. So you can probably already guess what is the impulse. If you apply a force for some time, you can change the momentum of a system, right? So the impulse is, we use I to represent it, but it's really just going to be the momentum transfer. Impulse I is defined to be, you apply a force over a certain amount of time, F dot into dt, the integral of the force, because the force may not be uniform, right, throughout the time, so you need to do the integration from start to finish. So conservation of momentum, if you take into account the momentum transfer, is going to be P final minus P initial equals the impulse, which is the integral of F dot into dt, which is also called the impulse momentum theorem. But it's not a new thing. It's really just expressing the same idea as a momentum conservation. Meaning, if you have a change in your system, the momentum changes, that is accounted by some force has applied on the system for some time, that is transfer. A lot of times, pretty much 90% of the problems we encounter, there is no impulse. Either there is no external force on the system, force is zero, or the force has applied for a really short amount of time. That's why we do collision problems, because collision problems happen so fast, the collision happens so fast, then you can ignore the impulse in that short amount of time. That's why we can ignore the transfer, so that for 90% of the problem we solve, the momentum final is equal to momentum initial, because there will be no momentum transfer, right? So the right-hand side is zero. So we simply start with this equation right away. P final equals P initial. So let's try to use that to solve some problems. Start with some checkpoint questions you guys have already done. Suppose you are standing on the cart, and this is a frictionless track. It's very important, it's frictionless. There's no, so you know that you and the cart, there is no external force on the cart, on the system. So will be no external force, right? so that the momentum of you and the cart will remain a constant. So before anything happens, you're just standing there, everything is at rest, right? But then you throw a ball off the cart to the left. Will the cart be put into motion? So now the system is you and the cart, which initially is at rest. So there's no momentum, zero momentum. Finally, if you throw a ball to the left, now which means part of the system is now going to have a momentum, right? Mass times velocity of the ball. But your entire momentum should still remain zero. In order to balance the momentum to the left, then you need momentum to the right. So if you throw the ball with some velocity, then the rest of you guys should have another velocity that is in the opposite direction of the cart. So it should be minus. So yes, it will be put into motion, right? And it will be moving to the opposite of the ball, which is to the right. Yes, it will move to the right. Right? Throw the ball to the left and the cart move to the right. Right, so this is a quick application of conservation of momentum. There is a variation of such a problem is if what if you bounce it off the wall that is mounted on the cart. Noticing that it will be a complicated process if you're trying to think about how, in terms of forces, right? When the ball hits the wall and pushes the wall, and how does that work? So instead of doing that, if you focus on conservation of momentum, again, this is exactly the same problem as before, is you only care where is the ball flying off at the end, right? Eventually, the ball is flying off to the right. So eventually, the cart with you all together should be moving opposite to the ball, that is to the left, right? If you only focus on the ball that is has a momentum to the right, finally, then the rest of the system should have a momentum to the left, so that momentum still remains a constant. This is conservation momentum. Initially, everything is at rest, so final should also be at zero. The only way for that to work is that the part of your cart momentum and your ball's momentum are add up to be zero. So they have to move to opposite directions. So the answer is yes, it will move to the left. Again, there is a similar question. Perhaps we can, let's say you don't really know what's going on. All you can see that there is a magic black box or there's a curtain that blocking your view. You don't know what's happening behind the curtain. All you can see is there's a ball flying off, right? So can you predict what's going to happen to the cart? Like I said, the complicated process, whatever happens behind the curtain doesn't matter. All you care is eventually the ball is having a momentum to the right. So the rest of the cart should have a momentum to the left, right? You don't have to worry about what's going on behind the curtain. So it's exactly the same problem as before. Whether you can see it or you couldn't see it shouldn't change the physical result. So the answer is yes, if you see a ball flying to the left, to the right, then the rest of the cart definitely would move to the left, so that the momentum remains the constant, according to conservation momentum, right? There should be no momentum change because there's no friction. There's no impulse, right? So these series of questions, you can see it's a very quick application of the conservation of momentum. We use this idea a lot to explain all kinds of questions. So for example, in your pre-lecture, there is a astronaut example, right? The astronaut is outside of the space shuttle and they want to get back to the spaceship. But the remaining constant, there's no speed. How could they gain some speed? Well, again, you decide to throw a wrench, throw a tool. So if you view the astronaut and the tool all together as a system, this is my tool. And initially there's no momentum. System remain at rest, right? No momentum. And I throw this part of the system, throw the wrench has a speed. So I will recoil and pick up some speed to the opposite direction. So I will throw the wrench tool to the opposite of direction of where I want to go. So I pick up some speed, I'll be able to go back to the shuttle. So this, you can see that again, using momentum conservation, that the momentum of the system remain constant, which is 0. So initially it's 0, finally after throwing, it's still 0. Okay. Again, this is another question from your pre-lecture. You can see that a lot of times, even though these questions look different, they are essentially the same. The throwing things, right, versus explosion is essentially the same thing. It's a one whole become many pieces. Whether I throw something away or something explode, it's the same idea. So you can apply, again, conservation of momentum. Here you have a bomb and exploded, split into 3 pieces. Again, you might wonder, wouldn't there be a huge force of explosion? Yes, there is. But again, that's not an external force, that's an internal force. So this internal force would not change the momentum of the entire system. So if your bomb originally, right, is at rest, 0 speed, so 0 velocity, 0 momentum. So whichever the 3 pieces fly, that their momentum should cancel out. Now, if they're equal, there seems like it equals split into 3 equal pieces. So the mass is same. All we need is a velocity to cancel out, right? So that momentum, mass times velocity, will cancel out. Let's look at whether this could work. If I look at B, you know that this up and down, these 2 cancels, but leaving a final momentum to the right. So this gives me a final momentum of the entire system pointing to the right. That's not okay. I need the momentum to be 0. P total should still remain 0, right? How about this one? This one looks like they could cancel, but if I look at the length of the arrows, this one is longer than this one, and these 2 add up to be diagonally, right? This one and this one, they'll add up to be diagonally, and it's going to be longer than this one going to the bottom left. And so eventually still have a momentum pointing to the upper right direction. These 2 do not entirely cancel, right? Because this one is bigger. So again, you have a non-zero momentum finally, and that's not okay, right? Choice A is okay. You can see that these 2 could add up to be to the right. And it also seems like in terms of the length of the vectors, so if you try to draw it a little bit more carefully, it's going to give you the same length as your vector going to the opposite direction. So it looks like these velocities could cancel out, give you a momentum final that is 0 that we want. So right, so we choose A. Okay, so you can see that I've applied the constant momentum multiple times over again. All of these cases start out with initial momentum of 0. So final momentum is non-zero. So you might wonder, someone might wonder, is this weird? I don't have any speed and then I gain some speed out of nowhere. So if you look at the final kinetic energy of the system, certainly you'll have some non-zero energy afterwards because each of the pieces are gaining some energy, kinetic energy. You add them together, they're scalars, they add up to be non-zero. They don't cancel like the momentum. So does this violate conservation of energy? You start out with no kinetic energy and you end up with a lot of kinetic energy. So does this violate conservation of energy? If not, where does the kinetic energy of these pieces coming from? Anybody would like to answer the question? Yes?
Is it potential energy?
Yeah, it could be the potential energy stored in the bomb. We can call it chemical energy or something. Yes, Eric said heat from the explosion. Well, heat would be a byproduct of that release of that energy. It's really the chemical energy stored in the bomb is transferred into or transformed into the form of kinetic energy flying And at the same time, part of that chemical energy becomes heat as well. Very good. Okay. So now it's your turn to use conservation of momentum to explain all of these phenomenons. And I promise at the beginning of the semester, we will be able to answer these questions using physics. It shouldn't be a long explanation, maybe just a sentence or two. So the first question, why would a gun recoil or why would a cannon recoil when you fire it? So anybody would like to help us answer that question? How can we use conservation of momentum to explain that?
The bullet has momentum, and so to cancel out with that the bullet's momentum, then the gun recoils.
Yes, very good. The bullet and the gun as a system remain constant to begin with. With the bullet regain some momentum forward, then the gun or the cannon would go recoil backwards. You have zero momentum final. Very good. Thank you, Tristan. The second one, how does a rocket work? We have explained how does a rocket work when we were doing Newton's third law. We can also explain how a rocket works using momentum. So anybody would like to take a shot at that?
Is it because the gas is coming out at a velocity, so the rocket has to like counter that, so it goes up?
Yes, very good, Alexander. It's exactly that. Again, you view the rocket and the fuel it carries as a whole system remain constant at first, part of the gas coming backwards, and then and the rocket would move forward to remain the constant momentum. Why do cars have chromosomes? Now this one I will write my conservation of momentum full equation. So hopefully we will be able to answer that. So that if there's a change of the momentum, that change must be done by a external force impulse. You apply the force for some time. So we will need to use this to answer that. Third question, why do cars have chromosomes? Anybody would like to try that?
Wait, what did you just say about time for the?
Apply the force over some amount of time. This is the impulse, which changed the momentum of the system, right?
Oh, is it because it increases the time of impact, basically?
Yeah, the chromosomes increase the time of impact because when if they have a collision, which means you definitely have a change in momentum. You're moving initially with some speed, and then you collide, you stop. So you definitely have to have a change in momentum. How can we make that change have minimal impact on the people or the damage to the car? Is this, let's say this apply a force of some time. Of course, this is not a uniform force, but let's just look at the average of the force during the impaction. This is the force on the car, right? So we're going to have chromosomes. You're increasing the time. Instead of stopping abruptly, you have some time to stop so that you are decreasing the force. The force will be smaller. Very good. Last question. Catching or trapping a ball is part of many sports. Coaches often say who catches well have soft hands or soft feet. What does that mean? Again, you can use conservation of momentum to explain this fact. Anybody would like to try that? It also uses this equation.
I think having this quote unquote soft hands or feet means that you somehow reduce the momentum. You reduce the momentum over a longer period of time, the momentum of the ball.
Yes, very good. It's the same as before. You somehow have a technique used because when we catch the ball, we don't just like catch like that. We grab it, kind of let it go for a little while, give us some little bit time to let it stop. So people who do that well are able to increase the time for the ball to stop. You're changing the momentum of the ball, of course. So increasing the time so it has a smaller force impact on your hand. Requires smaller force to stop it, so it's easier to stop. Yeah, so that's again very good application for using conservation of momentum. Okay, now we have a question for us to discuss. Two people on rollerblades throw a ball back and forth again. Ignore friction, which means there is no external force to you to consider. After a couple throws, what do you think these two people are they standing where they were? Are they standing further from each other or standing closer? Or are they moving away from each other or moving toward each other? I'll have you discuss this for a couple minutes and then when we come back, we can vote on. Okay, let's go for another 10 more seconds. So please wrap up our voting. Okay, any last minute vote? Okay, I'm gonna go ahead and close it. This is our results. So it seems like we are all agreed they are gonna be further away from each other as indicated by B and D. So the question is whether they are still moving or are they standing? So what do you think? Once I throw a ball to my friend that's standing across, right? I will right away. So what happens if I throw something?
If you have no friction, wouldn't you just keep moving, right?
Yeah, if I don't have friction, as it's saying, I know it's not real life. Eventually, we'll stop moving. But if you don't have friction, remember Newton's first law, you will maintain that velocity forever until an external force stops you or change your status of motion. Right. So we'd all agree conservation of energy. Initially at rest, I throw the ball. I'm gonna pick up the speed going the opposite direction. So, and my friend standing there eventually at rest catches the ball. So this is slightly different when you catch the ball. You're eventually having no speed, but once you catch the ball, you and ball become one together system. So the ball carries some momentum over. You're going to move back with that momentum. Is now just the ball's momentum is now being shared by you and the ball together. So the friend will also move backwards. And it's not going to slow down, right? And they throw it again, only make them moving faster the opposite direction, in that direction, throwing back to me. I catch it, only make me moving even faster to the other way. So they're going to be moving away from each other until they couldn't throw the ball anymore, right? D, very good. D is the correct answer. Okay. So let's use momentum, a conservation momentum, to do two types of collisions in our application. We can solve an elastic collision problem and or inelastic. So what is an elastic collision? So remember the conservation of momentum give us one equation. And knowing whether this is the elastic collision or inelastic collision will give us another equation. So combining usually two equations together, we can solve what we need to know. So for elastic collision, the definition is the kinetic energy of the bodies before and after collisions are equal. So you have this much kinetic energy before the collision happens, afterwards you have the same. You did not lose your kinetic energy to anything else, so that's elastic. Inelastic is where your kinetic energy is not constant before and after. Oftentimes, it's when you lose your kinetic energy during collision, right? You end up with less kinetic energy. So let's look at an example of an elastic collision. So for example, approximately, we never really have perfect elastic in real life, but good enough approximation are when the tennis ball hits the racket. So right, whatever speed the ball is moving, it's going to bounce back with the same speed. So kinetic energy wise, it's still same kinetic energy. And also playing pool, right? One of the ball will hit another, and if they're exactly equal mass, right, you're going to have the one that's being hit is going to carry over the exact same kinetic energy and the exact same velocity. So it's the kinetic energy remaining constant after before and after the collision. So let's see an example for elastic collision. It's called Newton's cradle. Okay. So what we're seeing here is that once you pick up a ball, this ball is perfectly elastic. So whatever momentum and kinetic energy perfectly transferred to this one. And you can see that's why this one have the same velocity as it going as this ball hits. This one stops completely, this one goes up. You can see they probably much go the same height, indicating they actually have the same speed when they go up, right? So now this person picks up 2, right? So any predictions, how many will fly up? If you release 2, How many will go up on the other side? Any predictions? Yeah, 2 will go up. Very good. Let's see. The middle one remains sort of just in the middle. Doesn't really move. So you pick up 3, the middle one will kind of just go back and forth as it would normally, like a pendulum. And the momentum transfer is happening between these 2 on the outside and these 2 on the outside. Again, the one with the 1 is a perfect demonstration of an elastic collision. Right? One comes in, the other goes out with the same velocity. So that's a demo for an elastic collision. So we can kind of model that or try to use that to answer a question. This is a question you have already done. There is a elastic collision between these 2 blocks. Maybe they're made of rubber or some material, but they collide elastically. So that gives you a very important information. So a green block of mass m slides on to the right, again, frictionless. There's no momentum transfer. Hit with another mass, red block m, capital M, initially at rest. So after collision, the green blocks is at rest now. The red blocks are moving to the right. So how does the 2 masses compare to each other? So not only the momentum is the same. So in this case, if we use conservation of momentum, P initial equals P final. Again, the system is M and M together. Initially, only 1 is moving, right? 2 is at rest, so 0 momentum. So the momentum of the system initially is just mv because the other one is 0. And finally, this one is 0. And what is this guy? So it's mv. Now, let's call this v naught. Now, this is v final. It doesn't really tell us what the momentum velocity is for v final. Okay, but another important issue. Okay, if that's all the information we know, we can't really tell how m is compared with little m, right? But it also tells us it collides elastically. So kinetic energy is also the same. So that's the other condition we can know because it's elastic collision. No, so kinetic energy before is really just the green block, 1/2 mv naught squared. The kinetic energy after is just the red block, 1/2 capital mv final squared. So if you compare these 2 equations, you realize now the velocity must be equal and the mass must be equal. That's the only way for these equations to work. Okay, so so this is like an example of the Newton's cradle example or the billboard, the pool that if you hit 2 objects of the same mass, one hits another. If they're the same mass, this one will stop completely and transfer 100% of the velocity to the other one. The other one will pick up with the same velocity. If your mass, this one is smaller, then it will bounce back. And if the green one is bigger than this one, it will continue to move together with the small mass. So that is something we know. Now, if you're given another question, they'll tell you m is bigger than m, then you know a bigger object hits a small one, then they're both going to be moving after collision. But if a smaller object hits a bigger object, then the smaller one will bounce back. Okay. So in this case, if one stops, the other moving, meaning that they must have the same mass. All right, so another question that you have already done. You have a box sliding on a frictionless surface. You can see that over and over again, we try to simplify our situation by looking at no friction. So which means we don't have to think about momentum transfer. They have a collision and they stick together. So what happens to the final kinetic energy of the system? So you can see that they stick together. So whenever you see something stick together, that would be a inelastic collision. There will be, the kinetic energy will no longer remain constant before and after. So the kinetic energy from here and the kinetic energy from here, they're no longer to be equal. And in fact, the kinetic energy here will be bigger than the kinetic energy final, because oftentimes if the kinetic energy do not remain constant, it will be lost. So there will be some heat generated, or if you have some damage to the block, that is also part of where the energy goes to. Right, so we have lost some of the kinetic energy during collision to heat. So whenever you see something sticks, that is a inelastic collision, and your kinetic energy final is going to be smaller. Okay. So there are more like explanations and process of how to solve this, but that could be, you can view the slides later on yourself. So let's look at for inelastic collisions, where we said when the kinetic energy is not the same before and after, right? We are looking at one particular type of inelastic collision where we can solve. It's called perfectly inelastic. It's saying means that it's 100% inelastic, because that gives us one more condition, is when the bodies are sticking together after collision, like the one we just saw, or like a car crash. Unfortunately, if they stick together and move together, and that's total inelastic, perfectly inelastic. Because if it sticks together, that gives us one more condition. What is that condition? Is that both of these two objects will now moving with the same velocity. If they're moving with two different velocities, we don't have enough equations to solve. But if they're moving, sticking together and moving with the same velocity, VA final is equal to VB final. Oftentimes we can solve the problem. So to summarize, for elastic collisions, we use, of course, Pi equals P final, conservation momentum, and we use another condition that is particular, belongs to the elastic collision, that kinetic energy remains constant. We use these two equations that oftentimes help us solve problems. Now, and then another type is going to be a perfect inelastic, that obviously we still use conservation momentum, but we have one extra condition, is the final energy of the two objects is the same. So each of these type of collisions will use two equations. One is obviously conservation momentum, and another one is the condition particular to the type of collision that they are. So is either elastic we're going to solve, or perfectly inelastic we're going to solve. So now let's look at a demo. Before we look at the demo, maybe you guys could predict what's going to happen. Look at the differences between elastic versus inelastic collisions. So let's say we have a demo called happy ball versus sad ball. To have one like a pendulum with a ball attached to a string, and you can use different materials for ball. You can use a really bouncy rubber material that's called the happy ball. So when it hits something, it bounces right back. So when it hits something, you're going to have an elastic collision. Or you can have a sad ball. When it hits something, it just lies there. So we use two different materials, and we're trying to knock over this piece of wooden block. Okay, so we try to release it and then see which one can knock this over more easily. So this is a question I want you to predict. So we release them from the same height, the happy or the sad. Which one is more likely to knock over the block? Okay. I'll give you a couple minutes to discuss, and then after come back, we can look at a demonstration together, okay? All right, so 10 more seconds. If you haven't voted already, please do so. Okay, all right. Any last minute vote? Okay, I'm gonna go ahead and close this. Let's look at the voting results. It looks like we are pretty much tied between A and B, slightly more than the choice C. Okay, so let's take a look at the demo to see what it's going to be.
All right, today I want to show you a little bit about elastic and inelastic collisions. Right here we have a mallet, which has two different rubber ends to it. One says happy, and the other one says sad. What we mean by this is the sad one, when it hits this surface, is going to just not bounce back. But if I flip this around, the happy side is the side that when it hits the object, it bounces back. Now, if I swing this mallet back far enough and release it, one of these is going to make the brick fall over. Which one? The happy side, the bouncy side, or the unhappy side? Well, let's try it.
Okay, so 1 second. I think your screen just froze. Let me redo this one more time. This is the happy side.
That one did it. On the other hand, if I switch it around so that the sad side is facing, let's try to reproduce this as much as we can from the last time. Pull it back as far as we dare, release it, nothing happens. Why does this happen? One way we can think of it is that when the sad one hits like this and stops, it's only half of the impulse that is given when the other side hits and then bounces back. We can think of the hitting as imparting some amount of impulse, and then the bouncing back as imparting the rest. All right, today I want.
Okay, so as the demo shows, the happy ball is more likely to be able to bounce off the block. Okay, and why that is? Well, using conservation of momentum, the block and the ball are one system, right? So before the collision happens, the momentum of the system is just really whatever. The ball is hitting the block with some velocity. So it's going to be whatever momentum the ball has. And finally, the ball is moving with a final velocity, and the block is moving with some other final velocity of the block. Okay. Now, this is conservation of momentum for both the happy ball or the sad one, right? Now, for both of them, they will hit the block with the same velocity because we release them from the same height. Right? It's really the same. But the difference is what happens to the final velocity of the ball. So the final velocity of the sad is going to be 0. But the final velocity of the happy is bounces back. So it's almost going to be exact same velocity but opposite directions. Exact same speed, opposite directions, so negative v. So with that different VF is going to produce a different result for the block, right? As I worked out more detail here, right? In order for the entire momentum still remain mv, if the happy ball finally is moving with a negative mv to this side, then the block has to be 2 mv, just so that when they add up, they're still going to equal to mv, right? But if it's the sad ball with a 0 final velocity, and the block was really just going to pick up the mv because 0 plus mv is equal to whatever initially they had. You see that? So the happy ball will be more likely to knock over this block. The explanation given in the video is more like the viewing the ball and the block are two separate, not entire system. So by looking at the impulse from the ball to the block as the impulse given to the block, so which is the impulse given to the block is a change of the momentum of the ball. So again, it's bigger for the happy ball. So I think maybe viewing from conservation momentum with two of them, the ball and the block as a system, might be easier, as I explained earlier. So the answer is A. You can see that you have already done this question, just slightly different wording in your checkpoint, right? You have a ball hitting a box, and one is bounces back, the other hitting it and just gets stuck. So this is like the happy ball version, this is the sad ball version. So which box ends moving faster? You can see that is exactly the same as before. The one that bounces back, the box has to move faster to still have the same momentum before and after during the collision, right? That is the conservation momentum. So if you view ball plus box as your system, so momentum initial is really just the momentum of the ball, because box is at rest, right? So it's going in mv, which is mv. The final is the ball. The ball has a different velocity, and the box have a velocity, right? Depending on the final, whether that's 0, as in 2, or if it's negative some velocity final, it will give you a different VF time for the box, right? So again, you can use conservation of momentum to explain it. Let's sum up what we have talked so far. For collisions, any kind of collisions, both elastic and inelastic, you're going to use conservation of momentum, which is a momentum initial equals momentum final. If the collision involving A and B, two bodies, then the initial has the momentum of one plus the momentum of another, right? That's all the momentum in of the system A and B. So A and B initial is equal to A and B final. So if you work it out with math, you will break it down into MA times VA initial plus MB VB initial is equal to MA VA final plus MB VB final. So momentum of A initial plus momentum B initial is equal to momentum A final plus momentum B final. So any kind of collision, you have that. But depending on what type of collision we're talking about, you have one more extra condition and one more equation that help you solve the problem. So if elastic collision kinetic energy doesn't change, so you add up all the kinetic energy before collision that equal all the kinetic energy after the collision final. For inelastic collisions, we are usually doing a perfectly inelastic when the objects stick together. So they have the same final velocity. So you either use this equation and this equation to solve elastic problems, or you will use, again, this equation and this equation to solve perfectly inelastic problems. Okay, so for today, the rest of today, we have one more example to do, and that is a perfectly inelastic collision problem. So let's look at what we have. We have two air carts, they have the equal mass. So these two carts have the same mass, which make it easier. You don't have to say MA or MB, they're just M for both of them, right? A moving toward B with speed V0, B initially at rest. The carts lock together during collision, and it's asking what is the speed of the cart after the collision? The first question. Second question is, after the collision, the air tracks turned off, so now there is some velocity, there is some friction. So the carts they lock together, they slide together with certain distance d, and then it came to a stop due to this friction. Given the kinetic friction coefficient mu, can you find the stopping distance? Okay, so you will see this type of problem a lot. There are two steps to it, and we can break it down into two sequential problems. The first problem is just the collision, not the sliding, right? So just the collision, we use conservation of momentum to solve it. And type of collision, we always try to describe the physics. So what is the physics? This physics is there is a perfectly inelastic collision going on between A and B. And the second type part of the problem is a conservation of energy problem. The cart are moving with some velocity and then they slide for some distance. You want to find the distance. Okay. Of course, you could use kinetics and dynamics to solve the problem. For the second part, you don't have to use conservation of energy, but it will give you the same result. And oftentimes, using conservation of energy is slightly easier to do. Okay. All right. So I'll give you guys a couple minutes to try to draw a picture and label your quantities and just think about how you might go about solving this problem before we do it together. We do have some time. This is going to be our last example. So why don't you take some moment, read the question and draw a picture and do as far as you can, go as far as you can, solving the problem, and then we will talk about it together. Okay. Let's draw a picture together. So, and while drawing the pictures also helps you to visualize the process. So I'm going to draw 3 pictures. Well, yeah, 3 pictures. Before collision. So what happens before collision is B is at rest. A is moving with some velocity, right? B not, A is moving. Cars lock together during collision. So I'm going to draw another picture. It's called after collision. We always draw a before and after picture for collision problems because it helps us to visualize the true state. This is like your conservation of energy problems, initial state and final state, right? So it's before collision, it's initial state, after collision, final state. So finally, they click, they lock together A and B, right? And with some final velocity together. Because A and B moving together, I'm going to use the same velocity to indicate velocity for both after collision. I'm going to call this a positive direction. I can draw a third picture. Is after collision, they slide for some distance. But for the first problem, I don't really need to draw the third picture. The first one, 2 pictures enough to solve the problem. Okay. Anybody have already solved the first question? What is the speed of the cars after the collision? Anybody did this one?
It's the momentum of cart A divided by the sum of the masses of cart A and cart B.
Yes, very good. Excellent. It turned out they're the same mass, so it's going to be give you half of the speed, right? Very good. Let's see how we get that answer. So the first question is, again, the system is A and B together. And our physics, well, we should decide our physics first. The physics is a perfectly inelastic collision. Okay, so which indicate we're going to use conservation of momentum. Okay, so we have our system, and your initial state is here, final state is here. We're going to use P initial equals P final. And there is no momentum transfer. I claim that because there are air carts, right? You know, only the air trap is only turned off after collision. Before it, it's very smooth because there's air. So there's no friction. There's no friction, there's no external force, which means there's no momentum change, right? So that's why I can use this equation, because there's no friction, okay? Okay, so momentum of A and B together initially is just mass of A times V naught of A. B is at rest, so it's 0 momentum, right? Now afterwards, A and B are together, so A and B together. So if there's different masses, you have to indicate them with different variables, but they're the same mass, so I'm just gonna write M for all of them, right? A and B together, V final. So you can see that because they are having the same mass, the mass doubles, so they're going to move half as fast as before, right? So the speed after is half of the speed of A. So that is my first question. You can see I did not need to draw the third picture, but the second part I do. So view this process as a first section and the second section. Now the collision is over, that happened. What happens next is they're going to slide. So now if you want, you can draw this picture 2 more times, because the final condition of the collision process is the initial condition of the next step, right? So it's here, they hit, and then they slide, right? So this is initial final, but from this process, this is like your initial again. So if you want, you can draw that picture 1 more time. So the second part of the problem, I'm gonna draw. Okay, for all I care is I see A and B moving together with V naught over 2. Now you can call that Vf still, but since you solved it, you can call it V naught over 2. Moving, and this is, what do I call it? I call this my initial state of the second problem. It's not initial state for the whole problem, it's initial state for the second problem. Initial state, which means right after collision. Right after collision. So they just started sliding, right? After collision, they slide for some distance of d. And they stopped. So this is my final state, that they stopped. Okay, so I'm gonna do again. So let's not forget conservation of energy. So we want the physics is conservation of energy. Again, we need our system is A and B. Okay, initial state, final state is figured out. Let's look at all these energy terms. Okay. Final, what is the final energy of the system when they stop right here?
There's no kinetic energy.
Yes, so I'm just gonna say 0. We don't have to think about potential because they're not going up or down. So I'm gonna say 0 and energy final. What is the energy initial when they at the initial state right here? What is the energy here? Is it just kinetic energy, right? It's just the kinetic energy of A and B together. So it's 1/2 mass A and B together is 2m. Velocity A and B together, moving with V naught over 2. Right? Everybody follows? Any questions so far?
No questions, Professor.
Okay, very good. All right, so that is the kinetic energy. It's going to be 1/2. So enough to be Oh, actually, no. (104) m v naught squared. Okay, input is 0, output is, you see there's friction. So the friction is doing work, and the work become an energy output, right? That's why it's stopped. So E output is going to be the positive, the absolute value of work done by friction. And you can see work done by friction is always going to be negative, right? Because your dot product between your force and your displacement is always opposite. So if you still remember how to calculate this, is negative friction, which is mu times n, normal force times your distance, okay, mu and d. So, but I only want to know what is the absolute value. So that's going to be mu mg, I'm sorry, mu normal force on both of them, right? Normal force on both of them is 2 mg because there's 2 of them, mu 2 mg d. Okay, so that is your energy output. So far, so good. This is very important. Okay, if you still don't know how to solve these type of problems, you should review the notes and ask me questions, because we definitely expect you to know how to solve these type of problems. Okay, so E final is, let's plug it in into here. E final is 0, E initial is the 1/4 m v naught squared is equal to E initial 0. Energy output is 2 mu mg d. So you can solve for distance. What is the question is, what is the distance, right? How far do they slide? Okay, so D is going to be V naught squared over M, and M cancels, as you can see, okay, over 8 mu g. That's your final result. So be careful that where here your system is A and B together. So that, right, when you do energies here, you need to use 2m. Right here, you need to use 2m. Right? If you use 1m in one of them, then you can see that you made a mistake, right? Because we're so used to plugging, okay, m as in mass, but here the mass is 2m, right? So just be careful. Another thing is you can see this is the velocity after collision. Even if it's the initial state of your second problem, but it's velocity after collision. It's like the final moment of your first stage is your initial moment of your second stage, right? So here, be careful of how you put in the velocity. If you say V initial, V naught, obviously that's wrong, because that is a velocity all the way up here. That is not the velocity you want. You want a velocity that's right here, right? You can see, you can use V final here, but then you still eventually plug in the V final that is calculated previously, right? Okay, so so we have finished all we need to do today. I have a solution typed out a little bit more, so you can look at my handwriting, or you can look at here, doesn't matter. We will continue to solve more energy and momentum problems on Thursday, all right? Now, if you have questions about what we did, feel free to ask. Any questions? You can do, if you want, a kinetic energy, a kinetic dynamics approach. In this case, your force acting on it will be your frictional force. So, right, so friction is going to give you F equals ma. Then you can find the acceleration. Friction is 2m mu 2m g is equal to 2ma. You can see your acceleration is going to be mu g. And then you can use that acceleration to find your distance, right? And you can do that as a practice on your own to see if you get the same result. You should get the same result, which is this velocity square of 8 mu g. Okay. All right. So that's all we have for today. We'll see you guys on Thursday. Okay. Bye, everybody.
Thank
Bye,
you, Professor.
Professor.
Have a good day.
Bye. Have a good day.
Thank you, Professor.
Thank you.